Okay, kids, we're back here. So, before we answer this question, what I'm going to have us do is take a look at this right here. This is the Earth. And this is an object on the surface of the Earth. Okay, I'm going to call that object M1. That's the object. Now, I want to calculate the force of gravity on this object. So one of the ways that I can calculate the force of gravity on this object is by using this equation here. Because this equation here, F little g is equal to mass times the gravitational field strength near the surface of the Earth, it works if and only if the object is near the surface of the Earth. That's it. But there is another way of calculating gravity, which is called universal gravitation. By the very name of it, universal, it means it must work everywhere. Is the surface of the Earth part of everywhere? Yeah. If everywhere is everywhere, then that's part of everywhere. So that means this has to equal big G, M1, M2, all over the distance between object 1 and 2 squared. You remember this? Okay. Well, kids, if this equation works and this equation works, it means that, and I'm only going to look at magnitude here. I'm only going to look at magnitude. It means they have to give the same value, right? Physics has to be consistent. I can't get a force of gravity calculation using one equation and a different force of gravity calculation for some other equation. It can't be. We have to get the same answer. Are you guys okay with that? Okay. So that means this would be, oopsie, I hate when that happens. I don't know why it does that, but it does. So here we go. That means mass of the first object times G must equal big G, mass of that first object, times the mass of the Earth, divided by how far apart they are from each other, center to center. Okay, I mentioned that in our notes, center to center. But so if you look back at the diagram here, the center to center distance between something on the surface of the Earth, right, and the middle of the Earth, give or take a few meters, even if you're on top of the Skylon Tower or the CN Tower, this distance, for all intents and purposes, is the radius of the Earth. The radius of the Earth is like millions of meters. So if you add a few hundred meters or even 1,000 meters, is that really going to change that number a lot? No, it's not. Won't even be near the same order of magnitude. So I can feel confident in putting in here radius of the Earth squared. So that means if I look here, I can cancel this out. And I get the gravitational field strength near the surface of the Earth is equal to G times the mass of the Earth all over the radius of the Earth squared. And if you were to put in G, you could try this later. If you put G in, 6.67 times 10 to the negative 11, right? Newtons meters squared or kilograms squared. Then multiply that G by the mass of the Earth, press equals, then divide that product by the radius of the Earth squared. Do you know what number you must get? What must that number be? Yes, Lonnie? 9.8 newtons. It has to be 9.8 newtons per kilogram. And you try it, that's what you'll get. Okay? So what's really important about this is I can convert this into what I call a general equation. Where now here's the Earth and here's an object, right? And now the object doesn't necessarily have to be on the surface anymore. Maybe the object is at a distance r from the center of the Earth, right? I can convert this equation and say, look, if I want to find out what the gravitational field strength is so far away from the Earth, right? I can say G is equal to big G. Why am I still using big G? Because we're in the same universe. Okay? Mass of the Earth. Why am I still using mass of the Earth? Because I want to find the gravitational field strength of the Earth. It's just not the gravitational field strength on the surface. It's the gravitational field strength where? At this distance. So if I look at number 8, it says, what is the gravitational field strength at a place 220 kilometers above Earth's surface? That's your R. Your R is 220 kilometers, right? Or it would be 2.20 times 10 to the 3, right? Kilometers. Times 10 to the 2, sorry, kilometers. Because I moved the decimal over twice. So 2.20 times 10 to the 2 kilometers. I don't like kilometers. Kilometers means 10 to the 3. So 2.20 times 10 to the 2. A kilometer gives me 10 to the 3. And I get 2.20 times 10 to the 5 meters. That's what this is, this portion of it. But I still have this portion right here. What's that portion? What's that called from the center of the Earth to the surface? Nobody knows? Yes, sir. Radius. Yes. Radius of the Earth. So you got to somehow calculate the entire distance. That's your R. It's still the Earth. It's still our own universe. And you will find the gravitational field strength when you're that far away. Now, just from the work you've done on gravity already, is the gravitational field strength when you're farther away from the center of the Earth than the surface of the Earth, is it going to be weaker or stronger out there? Yes. Weaker. Is this helping you? Okay. Bye, kids.